Hi, I'm Philip Rowe, and I'm doing a Bachelor of Electrical Engineering in Honours with a specialty in Information Engineering and AI. This presentation will contain an introduction and general summary, a description of the background knowledge to the thesis, experimental details, results, a discussion, and a final summary of achievements. In this thesis, we study medical report generation using deep learning. Report generation is where a medical image is input to a system and the output is a truthful textual summary emulating that of a radiologist. This thesis improved on existing methods of autonomously generating medical reports, demonstrating a strong 30% improvement to baseline and a very strong 15% against similar contemporary methods. Specifically, we used a vision transformer feature encoder feeding a memory-driven transformer encoder-decoder model to generate chest X-ray reports. I'll now walk through the background knowledge and how we achieved our excellent results. So what is report generation? Report generation is meant as an efficient tool for doctors to reduce error rates and improve patient outcomes. The quality of reports currently generated under the very best schemes to date have a calculated F1 score of around 55% of a radiologist. We do report generation in a machine learning context by understanding mathematically what is an image, or what is in the image, and then how to describe the things in the image with language. We separate these tasks into the feature encoder task and the language encoder and decoder sections. So what is a feature encoder? A visual encoder or feature extractor, a feature encoder, is the section of a computer vision model that learns how to represent the image mathematically. Feature encoder extraction is generally done with convolutional neural networks, which are perceptrons applied to the 2D domain. They perform 2D autocorrelation, and we can use stacks of these learnable convolution kernels to encode native 2D knowledge in these deeply stacked convolutional neural networks. Each convolutional kernel encodes some low-level knowledge, and the stacks can encode more complex aggregate knowledge for use downstream in the language models. Text generation models are generally a text model generating words and sentences it sees as most likely according to the data it's being fed. The classic way to do this was to use a recurrent neural network which uses time steps to repeatedly generate new words from the feature map's input while keeping track of what they have been already generated to allow them to make these whole sentences. At each time step, one of these networks picks the word it thinks is most likely to come next and builds up its text output. What is a transformer? Unlike RNNs, transformers don't use time steps, but generate all output tokens in parallel while still attending to proper textual structure. Therefore, they're faster to train and scale up on modern GPU hardware. Furthermore, transformers' ability to decode all outputs simultaneously allows them to model complex dependencies across the input and output. This means they can learn dependencies across the entire image without localization, and encode this image into the output with complex codependent sentences. The original transformer was a French to English machine translator, but the architecture can be applied to any sequence-to-sequence conversion, such as the feature space to text as shown here. Current models for report generation. Most image-to-text models are designed with small, single-sentence captioning in mind. For example, the man throws the ball to the dog. In the medical context, more complex information needs to be extracted from the image and then expressed, and so to achieve good performance, more effort is required. Other sources of information, like patient presentations, nearest neighbor sentences, and pre-trained CNNs on mesh terms, can be used. With RNN and transformer canonical models alike, we often incorporate memory or deeper and more specific reinforcement rewards for the model to attain good performance in this more difficult task. We are going to use one such model as our language encoder-decoder called R2Gen. While this diagram may seem daunting, it's the same feature space to text mapping using an encoder and decoder as before, as we can show. R2Gen incorporates extra parameters we call memory outside the normal transformer architecture that helps it to encode more intricate information about the medical reports it learns from. Issues with current models. The current examples of CNN-RNN and CNN transformer models are very similar to the simple models used for single-sentence caption prediction, such as here. Memory and other augmentations only make small tens of percent gains. Performance of these models on the report generation task, which is a maximum 55% F1, is far below performance on the more simple datasets, where they can get up to 95% exact matches. A radical architectural shift is required. Our experiments. While transformers are most natively applied to language modalities, recent research has expanded on their use across multiple domains. They're Turing complete, and they can emulate any function, for example the function of convolutions when applied to images. They have more modeling capacity per parameter than CNNs, and so vision transformers were born. Google Brain's VIT and SWIN transformers are based on transformer architectures as the primary modeling component. And we apply vision transformers as the image encoder for the medical report generation task. We apply our changes to the performant baseline model R2Gen, changing the ResNet 101, a classic and mature CNN design, for a VIT vision transformer or SWIN transformer architecture, and compare our performance across a variety of current language metrics. We call our architecture R2Gen Full Trans to reflect that it has purely transformer architectural components. The architecture pioneered in this thesis is an end-to-end pure transformer model for medical report generation with vision transformer feature extractor, transformer language encoder, and memory-augmented transformer language decoder. The images are first encoded to a feature space by the vision transformer before being mapped into a latent language representation space at the language encoder. The language decoder learns to decode this latent language representation into our desired reports. We compare ResNet, VIT, and SWIN across learning methods and hyperparameters. Our results. Our improved networks achieve 30% better cited performance than baseline. The vision transformer and VIT transformer make similar gains over CNN baseline and demonstrate the promise of transformer feature encoders. Discussion. Transformers have n-squared complexity with input size, and much research is dedicated to reducing this to linear or sublinear. Implementational gains are still being made through gradient checkpointing, compilation optimizations, fused operations, and more. Baseline performance is troubling for nearest neighbor and beam search CNN RNN schemes, indicating that these constrained, nearly true answers can still get high scores by the metrics we used. Perhaps better metrics need to be used, such as CheckSpurt. CheckSpurt and CheckSBurt metrics directly measure clinical accuracy and should be applied to all future research for true clinical comparisons. CheckSpurt's still not a perfect metric and can be expanded upon as with CheckBurt or more native natural language inference tools such as BERT-score. The fusion of meshed memory transformer, BERT-score, reinforcement learning rewards for entity matches, clinical metric judgments, and CheckSpurt, all used by Mira et al., represent the holy grail for pure transformer applications, and we should really apply transformer feature extractors to this. The closest work, 9 in blue, only improves on baseline by less than 10% and uses a much more shallow network with 3 layers for encoding and decoding, while I use 12 plus 3 for encoding and the same 3 for decoding. We achieve superior performance and suspect this is due to improved depth and separation of feature and language encoding sections. In addition to improved transform models, we have more parameters at 122.4 million, and using the larger Mimic CXR should also promise to be a simple scaling method for better performance. A motivation and achievements recap is I sought to apply the latest developments in transformer feature encoders to develop deeper, larger models for the report generation task, and we achieved excellent results. It's a new research area, and the demonstration of promising results shows a strong direction for the future. In summary, I've proposed a novel, purely transformer architecture. I've improved the current best baseline performance in medical report generation by 30% CIDR. I've expanded on future research directions with strong promises for human approaching performance. Thanks very much for listening.